is a branch of mathematics that deals with the calculation of instantaneous rate of change. This aspect, which deals with the calculation of instantaneous rate of change, is called differential calculus, or we call it differentiation. Calculus also deals with the summation of infinitely many small factors so as to get the whole part of that summation. And this aspect is called integral calculus, or we call it integration. Now, that means that we have been able to establish that there are two major branches, two major topics that establish calculus. The integral calculus, which is called integration, and the differential calculus, which is called differentiation. Now, these two topics made up this particular topic called calculus. Calculus is widely used in our modern world. One of the fields that make use of calculus largely are machine learning, artificial intelligence, data science, finance, economics, and actuarial science. The first aspect of calculus we are going to be explaining to ourselves is called differential calculus, or we call it differentiation. As we have explained earlier, differentiation deals with the rate of change of variables. How one variable changes with another variable, how one variable affects another variable. If you are familiar with your graph plotting, you will observe that your y is dependent on x. The value of your y, which is the output of your graph, is dependent on the input, which are the values of x. So x is the independent variable and y is the what? Dependent variable. So as x changes its values, then y also changes its value. To make it more practical, the rate of change of variables will be well understood if you consider an athlete that is running a race. If you want to determine the speed of that athlete, the speed of that athlete will be determined from two variables, and that is the distance of the athlete that he or she covered in a specific time. So the rate of change of distance, which is dependent on the time taken to cover a distance of that track, will give us the speed of that runner. So the rate of change of variables, how one variable changes with respect to another variable, is studied under differentiation. To understand differentiation mathematically, we have to go back to our basic understanding of gradient of a straight line. Let me bring that to reality. If you plot a graph will always have the two axes, the y-axis, which is the vertical axis, and the x-axis, which is the horizontal axis. And let's assume that we have a straight line graph which does not intersect. It's a straight line graph. It doesn't mean it just plotted like this. It's an assumption. And on this straight line graph, we are expected to find the gradient, or we call it the slope. Then we have to choose 2 points on that straight line graph. And with these 2 points you have selected, you will have selected the point on x, which is called x1. You will have selected the point corresponding to what? S2 here. Because for every Cartesian point, they are bounded with 2 coordinates. This is S1, Y1. This is S2, Y2 for every Cartesian point. So it means that you have selected, if you select P and Q, it is bounded with 2 points. If you select Q, it's also bounded with 2 points. So in that case, we have our x, we have our y. Then you can get the intercept of the 2 points this way. Here you have gotten that there will be an increment in the x-axis, which we call delta x, changing x. There will be an increment in the y-axis for the what? The y1. This is going to be y1, and this is going to be what? y2. And this is called delta y. So based on our calculation of slope, we know that our slope is denoted with n, and that is change in y, which is delta y, all over change in s, which is delta s, and this is y2 minus y1 all over s2 minus x1. Now this concept of slope explained in practicality, it explained in real mathematics language what differential calculus is talking about. It's talking about the changes that you have in y, which is dependent on the changes you have in x. because y is a dependent variable on x. As x changes, what happens here is that when you are looking for the increment in s, when s was y1, y will be y1. But when s changes to s2, then y will change to s2. So increment in s produces increment in y. Decrement in s produces decrement in y. And that is the concept of differential calculus. Let's give ourselves an example to explain that. Let's assume that we are given a graph, or we have plotted a graph, and the graph gives us the value of s to be 2, 4, 6, 8. Of course, we can also have the x-axis. This one is y-axis. This one is also, let's say this one is 1, 2, 3, 4, for instance. This is my x-axis, for instance. And you have constructed, or you have plotted a graph that looks like this. You have plotted a graph that looks like this. Then you have to find the slope of this graph. One thing about the slope of a straight line graph is that no matter the point you are choosing on your straight line graph, the slope will always remain the same throughout that straight line graph. That's one attribute of a straight line graph. So let's assume that I have chosen my point S to be 2 and 4. So this is my S1, this is my S2, and then let's say this is my Y1, and then this is my Y2. I don't want you to go beyond this. I don't want you to go beyond this, just a demonstration. And this is my y2. From here, we can get the slope of our graph to be, we are familiar with this calculation, changing y over changing x. That is, my y2, in this case is 8, my y1 is 6, my s2 is 4, my x1 is 2. This one is very good. This is 2. And this is also 2. So the slope is 1. So from these two calculations, we have been able to establish that differentiation is built from this basic understanding in mathematics. And that is the understanding of the slope of a straight line graph. The slope, every formula we are going to be developing in differential calculus is based on this formula, which is the rate of change in s, or the rate of change in y, which is dependent on the rate of change in s. Put this in mind. Then from there we will continue to deal with the gradient of curve graph, a line that is not straight. We have dealt with the straight line graph now. Then we move to a curve line, graph. We can also be asked to calculate the gradient of a curve line graph. Curve graphs are feasible in our quadratic graph, which produces a parabolic curve, a parabolic graph. So when you have a curve graph and you have to find the gradient of that curve graph, which is the case of rate of change of variables, because when you have a curve graph, the graph produces, non-constant variable, not constant values from between x and y. So when you have a curve graph that is not straight, for us to calculate the gradient of that curve graph, we are expected to choose only one point. Unlike the straight line graph that we just finished explaining, where you have to calculate the gradient of that straight line graph, and we said that the gradient, no matter the point you have selected, it is always the same across the points, because the straight line graph, it doesn't change. But a curve graph, which gives a slope p and different form and shape, different ups and downs, that will give us different method if you have different answer if you have selected 2 points. If you select 2 points, the value of your gradient will change based on the 2 points you have selected. So in that case, we don't normally select 2 points when we are looking for gradient of a curve graph. What we do instead is that we select only 1 point. Instead of 2 points, we select only 1 point. Then on that point of the parabolic curve, we are to draw a straight line graph, which is what? Which will be the tangent to that to that parabolic curve. And that straight line graph, which is the tangent to that parabolic curve, will not be used to calculate the gradient of that parabolic curve. Let me try to bring what I'm saying to you when I'm trying to bring it into reality. Let's assume that we have a graph, a parabolic curve that meets this graph at 5. And let's say that we have point P. And at this point P, you are told to draw a tangent to this graph. Then we can have a neighboring point Q. A neighboring point Q. Now from this point P, we have a tangent which will be used to calculate the gradient of this curve. Don't forget that this will also produce something like this. This one will give us change in S. This one will give us change in Y. Something is still here. This point Q, which is a neighboring point. So let's ask a question from this. From this graph, we can be told that let P, or let point P, which is X and Y. So let's assume this is the question you are given. This is a curved line graph, which is a parabolic curve. And this curved line graph, if we are to calculate its gradient, we said that we are to draw a straight line graph to it, and a straight line that we have drawn that meets this curve at the point P is called tangent. Okay, this is called tangent. Now this is x1, the first point of x. This is s2, the second point of x. In between x1 and s2, we have delta x, which is small delta. The one we used in our straight line graph was capital delta. This is small delta x. And we have our y, and the upper y, the changes in them is called delta y also. Now from this particular phenomenon, we would like to establish one of the fundamental formulas that we can use to calculate the gradient of this curve. Now, we are going to calculate it in two ways if time permits. The first way we are going to calculate it is that we have to consider the fact that from our graph, which is the y-axis and the x-axis, we can establish that our y is a function of x, isn't it? Y depends on x. Y is a dependent variable, s is an independent variable. It also implies that my y1 is a function of x1. x1 here produces y1 here, right? Then my y2, by implication, my y2 is a function of my s2, right? Then if I'm to find the slope of my graph, which is change in y, which is called delta y, over change in s, which is called delta x, is going to be y2 minus y1 all over s2 minus x1. Is it based on our straight line graph? We are calculating it from these tangents drawn to the graph. The formula for the slope of a straight line graph, which we have drawn to this curve graph here. And for us to establish this formula, we have to express our y as a function of x only. If you look at your neighboring point here, which is the q, we can have our s2 here, which is s plus change in s. The second point of our y, which will be dependent on our x, will be used as our s2 here. Then we have f is s plus change in x, instead of writing y2, which is the neighboring point here, minus the y1, which is f of s, instead of writing y here, all over change in x, because the difference of your s2 minus x1 is your change in x here. Then the next thing we have to know is that if we want to have this change in y and change in s, if we want to have change in y disappear, if you don't want to experience the increment in the y, which is dependent on the increment in x, let's say our change in s goes to 0. We try to reduce our change in s. The change in s, the increment in s, try to reduce it so that the opening here will close up. That is, the tangent will move closer to this particular to this particular curve. So we try to reduce this S2 to x1. When you try to reduce this S2 to x1, then y2 will also, which is changing y, will also goes to 0. Then when this 2 goes to 0, then we are going to have what we call total derivative, which is the y over the s. Instead of delta y, then we have total derivative y, total derivative x. What brings about this total derivative is when you limit your change in x, that's change in s, make it closer to 0, reduce this opening, reduce the difference between s2 and x1. Then we can write this one, which is f of s plus change in x minus f of s all over change in s. Now this is the first way to generate the formula that we call the first principle formula. First principle formula. This is the formula that we call the first principle formula. This is the first approach to generate it. You can also generate it with another approach. Let's look at that in the next lab. Yeah, considering the second approach in generating this first principle formula. Now, we have used the first approach, which is derived using the function of x approach. But in the case that we want to use this particular approach to generate the formula, we know that our y depends on x, which we call function of x, right? And then we can also say your y1 is equal to x1 depends on the function of x1. We are still using the same explanation. And y2 depends on function of x2. But we are not using that approach again. But what we want to establish is that my y2 here, which is y plus changing y plus changing y, in this case now, in my neighboring point q, it is dependent on f of s plus changing x. What this means is that we are considering this second point, which is my y2, and my y2 is y plus changing y, which is dependent on s plus changing x, based on the expression we have above. Then we can say this one will stand alone, changing y, f plus s plus changing x minus my y. And we have established here that my y is a function of x. So you return that here. That's f of s. We still go back to the initial point we established. Now this is my changing y. Then we can have it divided by changing x. So that means I'm dividing everything by changing s, because that was the original formula of gradient. So to have total derivative, changing y goes to 0, because changing s goes to 0. Then you have dy dx, which is the limit as changing s goes to 0. Then f of s plus changing x minus f of x all over changing s. This is still the same formula that we established. You can choose between the two approach, which one you prefer most.